Hello, in this video we're going to take another look at Lua and C++. Now you'll notice this is a part 3. If you've not seen parts 1 and 2, that's okay, they're not strictly necessary to enjoy this video. This video is a compare and contrast video where I'm going to recreate video 1 using the Sol library by the PhD. Hang on a sec, Javid, you're using somebody else's library. I didn't sign up for this. I know that's exactly what you're thinking. But as some of you may be aware, even though I've not been producing YouTube videos as frequently, I have been quite actively streaming on Twitch with my OLC Code Zone show. And in that show, I am building an editor of things and I am leaning heavily on Lua. If you've not caught those on Twitch, you can jump on over to the Javid X9 Extra channel and look at the uploads there. They have the world's most boring thumbnails, but if you peer inside, you can actually see there's a building of a 2D editor going on, and it's quite a sophisticated tool with which I wanted most of the internal tooling to be externally scriptable, and so I've chosen Lua. Now, as you'll see in this video, I'm quite happy to use Lua in its thoroughly naked form. In fact, that's what parts 1 and 2 of this series were really about. And whereas for small and very custom implementations of Lua, that's an acceptable approach, in reality, if you're going to use Lua in anger as part of a large project, don't mess about, and I'll save you watching this whole video if you want, just use the Sol library. Now, during this video, I'm probably going to call it Sol 3, Sol 2, Sol, Lua, whatever. I'm always referring to the same thing. And I suggest you jump on over to the GitHub repo and check it out by the PhD, because that's the first thing you're going to need to do. We need to download it. And here it is in my SDKs folder on my E drive. It's just a complete clone of the repository. I've also got one of the most recent versions of Lua as well. I've stuck that in the SDKs folder too. Now, if you recall when you're using Lua, if you're not prepared to compile it all yourself, you're going to need a binary implementation, but particularly on Windows. It comes as a DLL for your program to use. If you head on over to luabinaries.sourceforge.net, which is the official site supported by Lua, you can go and get the appropriate binaries and libraries for your platform. With all of that preamble out of the way, you can see I've got a blank program, just a basic int main. And in Visual Studio, I have configured the include paths to include the include folder for the Sol library and the include folder for the Lua library. I've also set a library directory for the Lua library too. What I'm aiming to show with this video is just how the Sol library can make our lives as C++ programmers much simpler. To do that, I'm going to take exactly the code and files we worked with in episode 1 of this series and re-implement them using the Sol library, and I think you'll be quite surprised at just how different they are and just how much of an improvement the Sol library is. And just to prove that that's the case, here is the embedding lua1.lua file from way back when, quite a while ago now. And in it we had some simple constructions, because we wanted to look at a few various features that we can do with Lua. We can treat it basically as a config file, we can create objects and pass those into the environment, we can call from the C++ program a Lua function, and we can call from the Lua program a C++ function, and that's as far as we got with episode 1. We'll do the same today, we'll also add in a couple of extras too. Let's start by looking at how we configure the C++ environment to use Lua. We started by including Lua, using these files, and linking to the library. Well, at no point are we going to manually handle Lua today. We're going to defer everything to the Sol library. So keep that in mind. We always work with Lua via Sol. Now, one of the nice things about Sol, and I'm a fan of this, is it's basically a header-only include. Isn't that nice? I like that sort of approach. And here I'm linking to the latest version of the Lua library. I'm using this bizarre pragma comment lib. For your platform and your compiler, you'll have to link to that library appropriately. I've defined for Sol that I want some of the safeties on. Sol is a deep and complex library, and it has all different levels of error catching and reporting. Right now, because we're developing and learning, I just want it to tell me everything that goes wrong. Recall that in effect, Lua is a complete virtual machine, and it only changes its state when we tell it to via our C++ program. In the first video, this is how we created a new instance of that state machine, and we had to open some of the Lua standard libraries. Sol is not much different. We create a Sol state, I'm going to call it Lua for this example, and we now tell it explicitly which libraries we want to provide. And for today, I'm using the base, which is standard stuff, some I/O so we can read and write, some math in case we wanted to do some sums, and the table. We probably won't even use most of those in these examples. Already this is quite an improvement, because we don't want to just open everything to the end user. Don't forget, we're effectively giving control of somebody we don't know access to our program. So that is actually an attack surface, and a surface which we want to reduce the size of as much as possible. We should only really let the user of our Lua scripts have access to the things they need to ensure our host C++ program can function properly. Once we've got Sol and Lua up and running, we probably want it to run some scripts. In the first video, we did this via the lua-l do file function, and we had to create a small wrapping function of our own. Let's just have a quick look at this. This is necessary because every call to Lua can potentially yield errors, and we want to catch those errors and somehow display them to our user. If indeed there was an error in Lua land, we can access what that error might be by taking it from the top of the stack. Now, this will be one of the last times you hear me mention the stack, because that's the first thing to note. The Sol sort of removes it from our equation, and it was also the most complicated part of the Lua interface. Here is the equivalent Sol code to load and execute a script. Firstly, you'll notice it's using exceptions. Now, this is entirely up to you if you want to use exceptions or not. One of the things about the Sol library is it's actually quite versatile. You can either use exceptions, like I have here, or you can look at error codes. I have the option to load the file in a safe manner. Should it fail to compile, rather than crash my program, I want it to yield as much information as it possibly can. Now, the script I'm going to compile today is exactly the same as the script from episode 1. So let's take a look. When I click Run, we see in the console, Lua file was read OK. If I set some sort of syntax error in the file and run it again, and I'm going to run it with the debugger to here, we can see it actually outputted an error message. Sol2, an error has occurred and has been passed to an error handler, and it tells me the line of the file, tells me what the symbol is, and tells me how to deal with it. That's quite nice. The next thing we did was read some simple variables. We treated the Lua script like it was a config file. And this worked by essentially searching for the symbol in the script file that we're looking for, in this case the variable a, and then we would check, is it a number, and if it is, we would grab it from the stack and we would manipulate the stack accordingly to yield that information. We're making a lot of assumptions here. Firstly, we're making sure that genuinely a does exist, and secondly, that it is in fact a number value. Now let's consider the Sol alternative. The only relevant bit of Sol code here is this fragment. What this command is doing is saying to our Lua state machine, please find the symbol a. If it exists, get its value. If it doesn't exist, return 0. No checks, no stack, no fuss. We can see that a is indeed a number, 5, and we can see that d is actually a string. In this case, we can be specific with the type that we want this get_or function to return. I quite like the get_or function because if it doesn't exist in the configuration file, then we can give it a default value. Let's just make sure this runs. We can see in the console output that we're outputting A, B, C, and D. Some of the more committed C++ heads out there might be frustrated at the fact that there's very little type information being supplied here, other than this one we're explicitly typing it as standard string. Well, we can be quite explicit with how we get these values too. In the script file, a is simply a number, 5, but we can explicitly cast it to a double with the get function. Doing things explicitly in this manner is quite useful if you need to inform the user that something is wrong with their script. This get_or function, despite not being quite as explicit as the code below, does perform some sort of existence check. Well, we can do that manually too. We can use what is called a Sol optional, and I'll come back to that in a minute, but this acts like a standard optional, and we can check for a variable's existence within the script just by seeing if it's mapped. So if we index our Lua object with the variable name that we're looking for, and it returns nothing, then we know that that variable doesn't exist within the Lua state machine. If I just remove these variables to stop the Lua compiler complaining, and change this a to an a1, we no longer have a in our script. So let's run our program. You'll see this time the program has crashed. Well, why has it crashed? If we look at our call stack, we can see that our explicit check searched for the value a, which doesn't exist, and so it's collapsed. Let's take this check out and run our program again. This time we can see that the file has read and executed OK, and the program has finished to completion. But we've not seen the message CPP S2 an optional double. That's because the value a did not exist in our script. Let's put it back in and run our program again, and there we go, the optional check has yielded positive, and we can see the value of a. It would have been nice to use a standard optional from the C++ standard library here, but for various technical reasons that's not the case, and the PhD does make an argument for this on his GitHub. And so sol optional is really a workaround for the following code, where we can use the get function on the returned Lua object, and if it exists, then the optional has some value, and if it doesn't, then the optional is null-opt. I quite like this. It's explicit, it allows the variable to exist or not exist, and it stays within standard C++ land. Let's take a look. There we go, works just fine. Everything in Lua is really some sort of mapping between a key and a value. That's just how Lua works. And so we can see here a player object that consists of various keys, title, name, family and level, and various values, Squire, Kieran, Wirral and 20. I'm sure that was relevant at the time of making the video. In Lua, this sort of construction is called a table. C++ doesn't really have tables. Its closest analogue, I suppose, would be a struct. And indeed, in part 1, that's exactly what we created. And then we needed quite a lot of complicated code in order to read those values from the Lua file. We had to find the name of the player object, and then we had to interrogate all of the key values individually, and this is without any error checking, keep in mind. And we had to be quite explicit with the types that we were reading back, and we had to manage the Lua stack. Once we'd done all of that, we simply displayed the output to the console. Let's do the same using sol. As you might have gathered already with sol, there's plenty of ways to approach solving the same problem, and I like that about a library because it allows you to be intuitive when it comes to writing the code, and you can choose the code that suits the mood you're in at that moment. I'm going to stick with standard optional just in case the player object doesn't exist. And you can see I want the type returned to be a sol table. I just interrogate my Lua object for the symbol named player. If the table exists, one of the things I can do is iterate through the key and value pairs. I can use a little auto for loop to do just that, and I can get the key and the value using sol object. Sol object is sort of the generic bottom of the ladder sol thing. It means you don't quite know what it is, but it can be everything and anything you want it to be. Each entry in the table as we iterate through it is a key and value pair. Now, most sol objects can be cast to other things, so if we wanted to see what the key is as a string, we simply do key.as and pass in standard string. Since we know what the key should be, we can now check the key's value and set the appropriate member of the player struct appropriately by casting the value component of the key value pair to whatever we need it to be. So we know in our script that name is going to be a string. So player.name, we read the value, but we say to sol, please return this as a standard string. Once we've read all of the key value pairs, let's output them to the console. Let's take a look. So here we can see in stage 3, a table equals Squire Kieran of Wirral, level 20. So that's one way of reading a table. However, it's always worth with the sol library just trying to see if something can be done quicker and better, because most of the time it can. Let's have another look. This time no standard optional, just going to be checking to see if the player object exists within the Lua state machine, and make it a table. And rather than iterating through the table, why not just try and index the table object directly? Well, you can do just that. And if we display the output on the console again, it was just fine. What we're starting to get a picture of is this get function and the as function, and being able to specialize to the types that we need it to be is proving to be quite convenient. We also know that we could check for the existence of these objects in exactly the same way we checked for the existence of individual variables earlier. Let's move on. So in the original episode, stage 3 was calling a Lua function from C++, and we had a function in our script called from CPP1, and we passed in 3 arguments, and we told Lua to output to the console those 3 arguments, and also do something with arguments 1 and 2 and return it. It's a completely useless function, but it's testing everything that defines what a function should be. In the original episode, we looked for the symbol called from CPP1 and we manipulated the stack to make sure that it was there. Then we pushed in the 3 arguments that we wanted to send to Lua, 5, 6 and a string, bwahaha. And we output from C++, hence the highlight here, to the console that we're calling that function in the Lua script. Once we've set up the Lua stack, we can then call the Lua function within the safety net of our check Lua function with the appropriate arguments and output its return value, hoping that it's there. Again, very little error checking going on here. It was quite involved. It requires that you get the stack just right. Let's have a look at how we do it with sol. So step 4, calling a Lua function. Done. And if you've ever looked at modern C++ and thought, I have no idea what all those templates are doing, I don't know what they're for and I'm never going to use them, well, it's the power of template C++ magic that's allowing this level of simplification. Here we've got our Lua object, we're looking for the symbol called from C++1, we're passing in 5, 6 and bwahaha as a string. Let's see what happens. So we can see at the end of our list here, Lua S4 called from C++1, 5, 6, bwahaha. And if we look at our script, just to confirm, there we are, Lua S4 called from C++1, etc, etc, etc. This function also returns a value. So how do we handle that? Well, thankfully, it's just as simple. We simply return the value into a variable we want that value to reside within. Let's take a look. So we can see at the bottom, CPP, called from CPP1, returned 30, and of course it multiplied the first 2 arguments, 5 and 6. Even though this clearly is a significant simplification from the original way of doing it, it's still not particularly safe. There could be syntax errors in this function, there could be runtime errors in this function. Calling a function is a risky business. Sol provides us with some tools to help us handle that risk. We can create a sol protected function object and extract that function object in the manner that you might expect by now. So if the function exists, then we know that it's safe to call, and I just pass in the arguments that I need. As you can see, it's also returning as well. It's the same function we were calling before. However, that call might have failed. If it did fail, then I shouldn't trust the value it's returned. But if it was valid, in this case I can check that it didn't fail, I can output the value returned. In fact, let's add in a clause for it failed. Let's take a look. Well, we can see at the bottom, yep, it's called the Lua function again, and it's displayed on our console the correct value. It's worked just fine. Let's now go and damage our function. I'm going to change this R3 to R4, which clearly isn't passed in. Now, I've got no safety net around these functions, so I'm just going to comment them out, so we don't actually crash our program. And run our program, and we can see this time call from CPP1 failed. Even though the function was found and existed, it just simply didn't execute properly. The function failed, but it might be nice to know why. Well, given that the return value from the function object wasn't the numerical value, you can see here it's some sort of sol object. In this case, a sol protected function result. In order to get the value of that result, we had to use the get function and explicitly tell it the type that we're expecting. Since the return value of the function isn't the value, it's some sort of object, we can interrogate that object to see what went wrong. So I assign my object to a sol error object, and then I can call the what function, like we did when we were loading the file. So let's see what went wrong. Well, it tells us on line 69, an attempt to perform arithmetic on nil value global R4. Well, we know that that is exactly what the problem was. R4 doesn't exist. It is a nil value. Let's put that back. Right, the next stage was to call a Lua function, which calls a C++ function hosted by our program. This bit is actually the same as what we've just done. we're just calling a Lua function. It's got a different name though this time. In the script, if we look at this stage, called from CPP2, makes a subsequent call to something called host function. And host function is going to be a function in our C++ program. If we look at the original code, host function had to be defined somewhere, and all it receives is the Lua state machine. We then had to do Lua stack manipulation to get values pushed to it. If we look back at the script, we can see we're calling it with the values that we're actually supplying from C++ to Lua, and then we're sending those values from Lua back to C++. If the function was successfully called, it would display on the console, then do some calculation and return that result back to Lua, which would then go and write it out on the console. This function itself would then take that result again and return it back to C++. It's a little bit confusing that, but the idea is to show sort of transactions happening in all possible directions. Our stage 5, I'm not going to get stuck in with all of the safety we've just done above. I'm very simply going to call our called from CPP2 function in the Lua script. We know that this Lua function is going to need a C++ function called host function. And previously we defined that function, and then after starting the Lua state machine, we registered that function in the global Lua space. It's actually pretty similar here, but we can do things with a modern C++ twist. I can inject into our Lua state machine by indexing our Lua object with a new symbol name. And Sol being entirely modern C++ compatible, and modern's a bit of a stretch these days, I'm just going to assign that directly to a lambda function. You may recall in part 2 of this series, where we used classes and started to talk to Lua via classes, that actually was quite a complex manipulation of pointers and static member functions. Sol magically takes care of all of that behind the scenes. Let's take a look. Here we can see stage 5 called from CPP2. So that's the Lua function being called. Lua then calls the host function. The host function in C++ is called from Lua and returns the correct value. This is very nice. This is very flexible. And that's the point we left it in the first episode. In fact, the second episode didn't really cover any more Lua interactions. It was more about how do we use Lua in a sensible way. However, for this particular episode, I want to continue with a few more tricks up Sol's sleeve. What we've just seen here is the ability to inject things into the virtual machine of Lua. We can do that with all sorts of things. In fact, you've always been able to do this with Lua, it's just previously it was quite tricky. Sol makes this delightfully and flexibly simple. In its simplest form, we create new symbols directly and assign them values. So here I'm creating a variable called entirely new variable and setting its value to 42. I've no way of testing if that actually ever worked, unless I read it back again from the Lua state machine's memory space. But a more creative way to see if that worked is to also then inject a function. And this function is in Lua called entirely new function and takes a single parameter, and it's going to take the entirely new variable and multiply it by that parameter. The script function of the Lua object provided by Sol allows us to execute new bits of script within the Lua state machine space. This means, of course, I can call my brand new function. Just as we have seen earlier, I'm going to pass in the value 3, and let's see what this new function actually returns. Well, it's returned the value x4 equals 126, which hopefully is 3 times 42. Since Lua first began, people have requested that somehow we can map the Lua environment into the C and C++ environment. Now that's something I don't necessarily think is a necessary part of being able to use Lua effectively with C++. In fact, overuse of doing so is probably a sign that your design is not partitioned very well. Nonetheless, there have been plenty of other libraries and attempts at bridging the two languages. And having played with a few, I can't say I care for them very much. However, Sol does make this very simple. I'm going to create a Lua equivalent of the player struct that we defined earlier. The new user type function allows me to map one of my C++ functions into some object called player in Lua space. I need to tell Sol what the constructors are for my player object, and I could have quite a few. But in this simple example, I'm just having the one. I then map the properties of my player object, in this case name, family, title and level, directly onto, oh there we go, thank you IntelliSense, directly onto the objects as they are in my C++ struct. There are some extra cool things I'm not going to detail in this video. For example, I can pass in new custom constructors, and I can also pass in getters and setters from Lua into C++. So if you access a C++ variable from Lua, it might actually take a different route than if you were setting it. That can actually be quite a useful thing, but not today. In my Lua script, I'm going to create a function called createPlayer1. I'm going to display on the command prompt that I've called this function, and then I'm going to do this. I'm going to create a local object P of type player. Now, Lua does have some notion of sort of object-oriented programming, but it's certainly a hack. In this case, I'm calling this new function. Sol has created all of this for me behind the scenes within the Lua virtual machine when I have created that new user type. This allows me to create a new instance of player. Now there's nothing in the constructor here, and that's because there's nothing in the constructor here. I can then use my object and its properties just as you would expect to, and I can set them directly and then return that object from the function. Since I can return the object from the function, I can use that to immediately initialize a C++ player object, in this case, simply by calling the Lua function createPlayer1. And just to make sure this works, I'll display on the console the same information I was displaying before. So just have a quick think about just how powerful this is for a second. I've created a mapping or a binding between a type in C++ and some pseudo object-oriented type in Lua. Sol has gone away and made all of that work in the background. I'm then calling my Lua function, but directly returning something which is compatible with my C++ environment. Let's have a look. And we can see here on the bottom line, player1 equals King Saladin of Sheffield, level 35. Now it goes without saying you can have nested types too. So if my player struct had some complexity to it, I could reconstruct that complexity in Lua space, and it will actually work as you expect it to work. I think it's an absolutely brilliant and powerful feature of the library. And a great companion to that power is the final step I'm going to talk about today. Using and manipulating standard library C++ containers in Lua. So these are things like vectors, maps, and lists. Sol has some wizardry in the background to bind standard C++ containers into the Lua virtual machine memory space. So let's create a standard vector of my player struct. I'm now going to inject a reference to that vector into my Lua state machine. I'm going to call it all players in Lua land. And as you can see, it's a reference to the vector. So we can prove that something's going to work, I'm going to output the size of this vec players vector straight away. And then I'm going to jump on over to Lua space and populate that vector from Lua. To do so, I'm going to need a Lua function called createPlayer2. I'm going to call that and I'm going to pass in the value 13. And then again, I'm going to display the size of the vec players vector. And just to make sure, I'm then going to iterate through my vector and display its contents one by one. So let's jump over to the Lua script. Here is my createPlayer2 function, and it's got a parameter n. I'm going to create n players and add them to the vector. I'm first going to display to the console that I've been called so we can track what's going on. And then my all players vector, remember this is the reference to the vector, I'm going to call a method clear. This is again something Sol has gone and constructed behind the scenes. This will clear the vector. I'm then going to iterate from 1 to n and add players returned from the createPlayer1 function up here. Change that to a 7. This createPlayer1 function returns an object which is directly mappable to my C++ struct, and I'm going to call this add function to my vector. So this is genuinely C++ stuff happening in Lua. Let's take a look. Well, we can see a lot more output has happened here. Starting at this line, we displayed the size of the vector and it's 0. We then called our function createPlayer2. CreatePlayer2 then in turn called CreatePlayer1 13 times, and it's indeed filled up our C++ vector with 13 elements, and all of those elements, they're all the same in this instance. We could have been more creative, I suppose, but there they are, all uniquely in our C++ vector. This combination of mapping and binding C++ directly to Lua is extraordinarily powerful, and something I am abusing to no end in my editor. And so there you have it, a very quick skirmish into the territory of the Sol library and interface into the Lua language for C++. I really have only demonstrated and scratched the surface of the power of this library. And I wish to express my gratitude to the PhD and others for putting it together. For me, it represents the perfect C++ library. It's intuitive to use without its documentation. It seems relatively feature complete. In my tests so far, I've not noticed any massive performance hits, and it's expedited the development of quite a sophisticated program I'm working on. That's all the boxes ticked. So if you've enjoyed this video, a big thumbs up please. Have a think about going over to the PhD and giving them a big thumbs up as well. Go and get the library and have a play with it. I'll put this source code on the GitHub. Come and have a chat on the Discord, and I'll see you next time. Take care. Bye bye.